Major Heinrich Wolf had been an artillery officer for 22 years. He had calculated firing tables for every German field gun in service. He had fought in Poland, where German artillery crushed outdated fortifications in hours. He had fought in France, where precision fire reduced the Maginot Line to rubble. He had fought in Russia, where his batteries destroyed Soviet positions across distances that made enemy commanders weep with frustration. Wolf understood artillery the way a pianist understands music. Every variable, every calculation, every limitation. What he was watching through his Zeiss binoculars violated every principle of artillery science he had ever learned. December 23, 1944. 8:47 hours, 6 kilometers south of Bastogne, Belgium. Wolf stood in the command post of the 18th Volksgrenadier Division Artillery Battalion, watching 3 American P-47 Thunderbolt fighters fly toward his position at perhaps 800 meters altitude. The morning was bitterly cold and perfectly clear. Excellent visibility. His battery of 4 105mm howitzers sat concealed in a tree line, preparing to fire on an American supply convoy moving along the road 3 kilometers west. Everything was ready. His crews were the best in the division. They had survived Normandy, survived the retreat across France, and now they were part of Operation Watch on Rhine. Hitler's final gamble to split the Allied armies and reach Antwerp. The P-47s were not an immediate threat. American fighter bombers passed over German positions constantly without detecting well-camouflaged artillery. Wolf watched them through his binoculars, waiting for them to pass so he could give the fire order against the convoy. Then the sky filled with black smoke. Dozens of explosions appeared around the 3 aircraft in rapid sequence. Perfect black clouds of shrapnel forming a dense killing zone exactly at the altitude where the P-47s flew. The American aircraft broke formation immediately, diving and turning desperately to escape. Wolf stared. Those were not German anti-aircraft guns. The nearest Wehrmacht flak battery was 12 kilometers away. These explosions were coming from American positions to the west. The Americans were firing at their own aircraft. No, not at their own aircraft. These were American guns firing American shells at German aircraft that had not yet appeared. No, that made no sense either. Wolf raised his binoculars higher, trying to understand what he was seeing. Every explosion occurred at exactly the same altitude, perhaps 750 meters, maybe 800. He could not measure precisely from this distance, but the consistency was impossible to miss. Each black burst appeared in a perfect horizontal plane, as if someone had drawn a line across the sky and ordered the shells to explode only at that exact height. That was impossible. Normal anti-aircraft fire created scattered burst patterns because time fuses were inherently inconsistent. You set a fuse to detonate after a specific time interval, you fired the shell, and you hoped it exploded somewhere near the target altitude. Variations in powder temperature, barrel wear, shell weight, atmospheric pressure, wind, humidity, all of it affected the time it took the shell to reach altitude. A fuse set for 800 meters might explode anywhere between 700 and 900 meters, sometimes higher, sometimes lower. That 200-meter variation made anti-aircraft fire largely ineffective against fast-moving targets. You compensated by firing massive barrages and hoping random chance put shrapnel where the aircraft would be. But what Wolf was watching showed no variation at all. 40 shells, maybe 50, had created a wall of explosions at identical altitude. Every single burst at the same height, the same precise killing zone. His hands started shaking, not from the cold. One P-47 took shrapnel hits. Wolf watched smoke trail from its engine as the pilot fought for control. The aircraft turned east, losing altitude, trying to reach friendly lines. It would not make it. The other two P-47s fled south, disappearing beyond the ridgeline. The entire engagement had lasted perhaps 20 seconds. Wolf lowered his binoculars. His mouth was dry. His mind was racing through calculations, trying to find an explanation that made sense. There was no explanation. What he had witnessed was impossible according to every principle of artillery fuse design. Unless the Americans had developed something completely new, unless they had found a way to make shells detect their altitude and detonate automatically at the correct height. But that would require a fuse that could sense its environment, a fuse that could measure distance to a target. That was not a mechanical device. That was something else entirely. His radio operator was shouting, "American counter-battery fire incoming." The convoy escorts had called in artillery support. Wolf snapped back to the tactical situation. His crews scrambled to their guns, preparing to displace before American 155mm shells arrived. Standard procedure: fire your mission, relocate immediately, survive to fight again. The battery displaced 400 meters north to a secondary position they had prepared the previous day. By the time American shells stopped falling on their original location, Wolf's guns were ready to fire from the new site. But Wolf's attention kept returning to those impossibly precise air bursts. His mind would not let go of the problem. That afternoon, Lieutenant Beck returned from a forward observation patrol with interesting news. His men had found an unexploded American shell half buried in snow near an earlier impact area. Beck thought it might be worth examining. German intelligence was always interested in captured American ammunition. Wolf and Beck walked to where two soldiers stood guard over the shell. It lay in a small crater, partially covered with fresh snow. A 90mm anti-aircraft round, approximately 60 centimeters long. The shell casing showed no damage. It had simply failed to detonate when it hit the frozen ground. Wolf knelt beside the shell and immediately saw something wrong. The nose section was not standard. Instead of a pointed steel cone, this projectile had a different front end. The nose appeared to be made of some kind of translucent material, not glass, something that looked like bakelite. Through the translucent material, he could see thin metal components inside, wires, filaments. He had never seen a fuse like this, ever, and he had examined every type of German fuse in service, plus captured Soviet and British designs. This was something completely different. The nose section was too large and too complex for a mechanical impact fuse, and the translucent material made no sense whatsoever. Fuses were steel, always steel. You did not put fragile materials in the nose of an artillery shell that would experience crushing acceleration forces during firing. Wolf's throat tightened. He stood up slowly, feeling suddenly cold in a way that had nothing to do with the December weather. He ordered 4 soldiers to load the shell onto a truck immediately. Pack it with blankets, drive carefully, no sudden movements. Transport it directly to division headquarters. He scribbled a brief report for the divisional intelligence officer, handed it to Beck, and sent the truck on its way. 3 days later, Wolf received orders to report to the field workshop compound. When he arrived, he found not just the divisional intelligence officer, but 2 engineers from Army Group B headquarters. They had driven through American artillery fire at considerable risk to examine what Wolf had found. The workshop bay was cold. Someone had set up a portable heater, but it did little against the December chill seeping through the walls. The unexploded shell sat on a wooden examination table under bright electric lights powered by a generator rumbling outside. The translucent nose section had been carefully removed. The internal components of the fuse mechanism were now visible. Wolf stopped walking when he saw what was inside. He stood completely still for perhaps 10 seconds, staring, not quite believing what his eyes were showing him. Vacuum tubes, 4 of them, tiny glass tubes no larger than a pencil, arranged in a compact cluster. Around them were other components he recognized from technical training. Capacitors, resistors, a miniature transformer, all of it assembled on a circular mounting plate, perhaps 4 centimeters in diameter. This was not an artillery fuse. This was a radio receiver built to fit inside an artillery shell. One of the engineers, a Hauptmann named Drescher, was speaking. Wolf heard the words, but his mind was still trying to process what he was seeing. Drescher repeated himself. This is a proximity fuse. It transmits a radio signal. It receives the reflected echo. When the signal strength indicates the shell is close to a target, it detonates automatically. The second engineer, Oberleutnant Fischer, was older, perhaps 50, with wire-rimmed glasses and ink stains on his fingers. He added more information in a quiet voice that made everything worse. The fuse contains a complete radar system, transmitter, receiver, amplifier, all miniaturized to fit in this space. It also contains batteries activated by centrifugal force when the shell spins during flight. The batteries power the electronics for approximately 25 seconds, more than enough time to reach the target. There is even a backup battery in case the primary fails. Wolf found his voice. How can vacuum tubes survive the firing shock? Drescher gestured at the disassembled components. The Americans use ceramic envelopes instead of glass. Ceramic that can withstand acceleration forces exceeding 20,000 times gravity. The internal filaments are reinforced with support structures that prevent them from breaking. We have been trying to ruggedize vacuum tubes for artillery applications for 3 years. We have failed every time. The tubes break. Always. The Americans have solved this problem completely. The workshop fell silent except for the rumble of the generator outside. Wolf stared at the components spread across the examination table. His mind was doing calculations he did not want to complete. Fischer opened a notebook. His hands were shaking slightly. Based on the component specifications we can measure, this fuse costs approximately 15 to 20 American dollars to manufacture. Perhaps more. We are not certain, because some of these components do not exist in German production, but the cost is justified by effectiveness. Standard anti-aircraft fire requires approximately 2,500 shells to destroy one enemy aircraft. With these proximity fuses, that number drops to approximately 100 shells. Drescher was pacing now. His boots clicked on the concrete floor. He stopped and turned to face Wolf. 25-fold improvement in effectiveness. 25 times fewer shells required to achieve the same result. The extra cost per shell is insignificant compared to the value of reliably destroying enemy aircraft. The Americans have changed the mathematics of anti-aircraft warfare completely. Wolf heard himself ask the question, how many of these are they producing? Fischer and Drescher looked at each other. Neither wanted to answer. Finally, Fischer spoke. Based on intelligence estimates from the number of proximity-fused shells encountered across all theaters, we believe the Americans are manufacturing between 30,000 and 40,000 of these devices every day. Perhaps more. Production has been increasing since late 1943. The workshop tilted. Wolf gripped the edge of the examination table to steady himself. He felt suddenly dizzy. 40,000 per day. He forced himself to think clearly through the shock. 40,000 miniature radar sets, every single day, each one containing vacuum tubes that Germany could not produce in any quantity. Each one representing a level of miniaturization that German electronics firms considered impossible with current manufacturing technology. And all of it being built by American factory workers and shipped across the Atlantic by the millions. Drescher continued talking, but his voice sounded distant. We have attempted to calculate what would be required to copy this design. The tooling, the specialized manufacturing equipment, the trained technicians, the testing procedures. Even if we started today with unlimited resources, we could not produce these fuses in meaningful quantities for at least 18 months. Probably longer. By then the war will be over. Fischer added one more detail in his quiet voice. The Americans began developing this technology in 1940, 4 years ago. While we were celebrating victories in France, American scientists and engineers were solving problems we did not even know existed. They were creating manufacturing processes for components we still cannot make. And they were doing it at a scale we cannot match. Wolf walked to the workshop entrance and stood looking out at the snow. His battery was firing. He could hear the distant thump of guns. His guns. Firing shells with mechanical fuses that had not changed fundamentally in 30 years. Firing at targets they would probably miss because mechanical fuses were inherently inaccurate, while the Americans fired shells that saw their targets. That adjusted their detonation point automatically. That turned near misses into kills. Drescher began packing the disassembled components into a wooden case. These pieces will go to Berlin for detailed analysis. Perhaps something useful can be learned. Perhaps German industry can adapt some of the manufacturing techniques. But we all know the truth. No one said what that truth was. They did not need to. Wolf returned to his battery that evening. His crews had displaced twice more during the day, avoiding American counter-battery fire. They were exhausted. 8 days of continuous fighting with minimal sleep. Ammunition stocks were running low. German supply trucks kept getting destroyed by American aircraft. He did not tell his men what he had learned. What would be the point? They would continue fighting because soldiers fight. They would fire their guns until the ammunition ran out, or until American forces overran their position. But Wolf now understood something that made the December cold cut deeper. Germany was not losing because of inferior courage, not because of inferior tactics, not even because of inferior numbers. Germany was losing because the enemy could mass-produce miracles. The Americans had turned radar into something you threw away after 30 seconds. They had made the impossible routine. And they were doing it 40,000 times per day, while German factories struggled to produce enough ordinary mechanical fuses to meet basic requirements. Fischer had mentioned one other thing before Wolf left the workshop. Something he said almost as an afterthought. We have also received intelligence reports that the Americans are now using these proximity fuses against ground targets, against infantry in defensive positions. The fuse can be set to detonate at a specific height above the ground, 3 meters, 5 meters, any height desired. The shell explodes in the air over the target area. Shrapnel rains down on soldiers in foxholes and trenches where they previously had protection. Wolf stood in the darkness outside his command post, watching his crews prepare the guns for night firing missions. Good men. Skilled men, veterans who had survived 3 years of brutal combat. And somewhere in the American supply system, millions of shells were being fitted with fuses that would explode perfectly above their heads, turning their foxholes into killing zones, making their skills and experience irrelevant against technology they could not see and could not fight. The mathematics were very simple: 40,000 per day, every day. While Germany produced perhaps 400 ordinary mechanical fuses on a good day, 100 to 1, in favor of the Americans. And the American fuses were not ordinary. They were technological marvels that German industry could not duplicate. The war was already over. The Americans had won it in factories and laboratories, while German soldiers bled in the snow, believing that courage and skill still mattered. They mattered, but not enough. Not against an enemy that could manufacture the future faster than Germany could manufacture the present. Dr. Werner Osenberg watched glass fragments scatter across the concrete floor of the Kummersdorf test chamber and felt his stomach drop. That was the 14th tube they had broken, attempting to replicate the centrifuge test. 14 tubes. Each one hand selected from Germany's best vacuum tube production. Each one carefully mounted in the test fixture. Each one subjected to the same acceleration profile that American proximity fuses survived during firing. And each one had exploded into worthless fragments within 3 seconds. January 8th, 1945. Kummersdorf Proving Ground, 40 kilometers south of Berlin. Osenberg was director of the planning office of the Reich Research Council. He had coordinated German weapons research for 2 years. He had worked with the finest scientific minds in Europe. He had overseen development of jet engines, guided missiles, and advanced rocket technology. He was not accustomed to failure, but he had been failing continuously for 6 days. His assistant, Dr. Klaus Hartmann, was already mounting tube number 15 in the test centrifuge. Hartmann was younger, perhaps 30, with steady hands and the patience of a man who had spent years in laboratory work. He checked the mounting clamps twice, verified the electrical connections, then stepped back from the centrifuge. "Ready, Herr Doctor." Osenberg nodded. He pressed the activation switch. The centrifuge began spinning, slowly at first, then accelerating rapidly. The electric motor whined as it drove the test fixture faster and faster. They needed to reach 20,000 times the force of gravity. That was the acceleration a proximity fuse experienced during firing from a 90mm anti-aircraft gun. The test fixture became a blur. The motor reached maximum speed. Osenberg checked the force gauge. 18,000 G, 19,000, 19,500. The tube exploded. Another sharp crack. More glass fragments hitting the safety shield. Hartmann made a notation in his log. Tube 15, failed at 19,700 G. Time to failure, 4.2 seconds. Osenberg walked away from the centrifuge and stood staring out the window at the snow-covered proving ground. 6 days, 15 vacuum tubes destroyed, and they were not even close to matching American performance. The American tubes survived 20,000 G easily. Some had been tested to 25,000 G without failure. German tubes broke consistently below 20,000. This was not supposed to be possible. Germany had the finest vacuum tube technology in Europe: Telefunken, Siemens, Valvo. These companies had been manufacturing radio tubes for decades. Their products were known worldwide for quality and reliability, and yet they could not build a tube that matched what American factories were producing by the tens of thousands every single day. Behind him, Hartmann was preparing tube number 16. Osenberg turned from the window. "No, stop." Hartmann looked up in surprise. "Sir, stop wasting tubes. We are not going to solve this problem through trial and error." The Americans are using a fundamentally different technology: ceramic envelopes instead of glass, reinforced internal structures we do not understand. We need the actual American components to examine, not German tubes that fail. Hartmann set down the tube he had been preparing. We have the American components, 3 complete fuses from captured shells. We have disassembled them. We have photographed every piece. We have measured every dimension. What more can we learn? Osenberg felt anger rising in his chest, an unfamiliar sensation. He was a scientist. Scientists did not become angry at data, but 6 days of continuous failure had worn through his professional detachment. How they manufacture them, the process, the tooling, the quality control procedures. We know what the components look like, but we do not know how they are made. And without understanding the manufacturing process, we cannot replicate them. He walked to the workbench where the disassembled American fuse components were laid out on white examination cloth. He picked up one of the ceramic vacuum tubes. Such a small thing, no larger than his thumb, and yet it represented a manufacturing capability that Germany apparently did not possess. General Major Friedrich Bauer arrived at 1400 hours, accompanied by 2 officers from the Army Weapons Office. Bauer commanded the anti-aircraft testing division. He looked exhausted, deep lines around his eyes, uniform rumpled. He had probably driven through the night from headquarters to attend this meeting. What is your assessment, Dr. Osenberg? Can we manufacture these fuses? Osenberg had been preparing his response for days, dreading this moment. He set down the ceramic tube and faced Bauer directly. No, we cannot. Not with current German industrial capacity. Not within any time frame that matters for this war. Bauer's expression did not change. He had clearly expected this answer. Show me why. Osenberg led the group to the examination table where the American fuse components were displayed. He picked up one of the ceramic tubes. Start here. These tubes use ceramic envelopes, not glass, ceramic. Germany has no facilities for mass-producing ceramic vacuum tubes. We have experimental programs. We have prototypes. We do not have production capability. Building the factories and developing the processes would require minimum 18 months, probably longer. That assumes no disruption from bombing. One of the officers, an Oberst with combat decorations from Russia, interrupted. 18 months? The war will be over in 18 months, probably sooner. Exactly, Osenberg said. He set down the tube and picked up one of the miniature capacitors. These capacitors use a dielectric material we have never encountered, some kind of polymer compound. We sent samples to IG Farben for analysis. They reported that it appears to be a specialized resin with specific electrical properties, but they cannot determine the manufacturing formula. Developing an equivalent would require extensive chemical research. Another year minimum. He gestured at the battery assembly. This uses a centrifugal activation system. The battery is completely inert during storage and transport, then activates instantly when the shell is fired and begins rotating. We have no battery technology that reliable. Our batteries either activate prematurely or fail to activate at all. Bauer was studying the components carefully. Each one individually is difficult. All of them together? Impossible with current resources, Osenberg said. Every component represents a manufacturing challenge we cannot meet. Not because German engineers lack intelligence, not because German workers lack skill, because we lack the industrial infrastructure the Americans have built specifically for this purpose. Hartmann spoke from his position at the test bench. May I add something, Herr Generalmajor? Bauer nodded. Hartman opened a notebook filled with calculations. Based on intelligence reports, the Americans are producing between 35,000 and 45,000 of these fuses per day. The estimates come from the number of proximity-fused shells encountered in combat across all theaters. The actual number could be higher. The workshop fell completely silent. Bauer stared at Hartman. Repeat that number. 40,000 fuses per day. Perhaps more. Bauer turned to Ozenberg. Is this possible? Ozenberg had spent 3 days verifying those numbers, cross-checking intelligence reports, analyzing ammunition expenditure data, running calculations. He had wanted desperately to find an error, to discover that the estimates were exaggerated, but every analysis confirmed the same horrifying conclusion. Yes, it is possible. It is happening. The Americans have distributed production across multiple factories. Western Electric, Eastman Kodak, Sylvania Electric, Raytheon, and approximately 15 smaller contractors. The vacuum tubes are manufactured by specialized firms. Final assembly occurs at several locations. They have deliberately spread production to ensure that bombing cannot disrupt the supply system. Bauer walked to the window and stood looking out at the proving ground. When he spoke, his voice was quiet. 25 years I have worked in artillery development. I have designed fuses. I have tested fuses. I believed German artillery technology was the finest in the world. Our time fuses are reliable. Our impact fuses are well engineered. He turned back to face the room. And now I learn that the Americans are mass-producing electronic fuses that make everything we build obsolete. 40,000 per day. Do you understand what that number means? Ozenberg understood exactly what it meant. He had been living with that understanding for 6 days. It means the Americans are installing 4 vacuum tubes in every fuse. That is 160,000 vacuum tubes per day, dedicated solely to disposable artillery fuses that will exist for 30 seconds before being destroyed. Germany produces approximately 600 vacuum tubes per day, total for all applications. Military radios, communications equipment, everything. 600 versus 160,000. The industrial gap is not measurable in percentage terms. It is measured in orders of magnitude. The Oberst spoke again. Can we at least understand how they work? Document the technology for future use? Hartman answered. We understand the basic operating principle. The fuse transmits a radio signal at approximately 180 to 220 megahertz. It receives the reflected echo. When the signal strength indicates the shell is close to a target, typically 15 to 30 meters distance, the fuse triggers detonation of the main charge. The system is elegant in concept, but elegant concepts do not help us if we cannot manufacture the components. Ozenberg added more disturbing details. The fuse also includes backup systems, a secondary battery in case the primary fails, redundant triggering circuits. The Americans have engineered reliability into every aspect. These are not experimental prototypes. These are mature production devices, thoroughly tested, proven in combat. They represent years of development work that occurred while we were focused on other technologies. Bauer returned to the examination table. How much does one of these cost to manufacture? Hartman consulted his notes. Based on component analysis and estimated labor hours, approximately 15 to 20 American dollars, perhaps slightly more. $20 for a disposable fuse, Bauer said. He picked up one of the ceramic tubes and held it up to the light. $20 for something that will be destroyed in 30 seconds. The Americans consider this acceptable because the fuse works. because it multiplies the effectiveness of every shell by factors of 10 or 25. The extra cost is insignificant compared to the value of reliably destroying targets. He set down the tube. What about using these fuses against ground targets? We have reports from the Ardennes. Ozenberg had been dreading this part. Yes, we have confirmed that the Americans are now using proximity fuses against infantry positions. The fuse can be set to detonate at any predetermined altitude, typically 3 to 5 meters above ground level. The shell explodes in the air over the target. Shrapnel strikes downward into foxholes and trenches. He pulled a folder from his briefcase and opened it. This is a casualty analysis from a Volksgrenadier division that came under American artillery fire using proximity fuses. Casualty rates were approximately 3 times higher than from conventional artillery fire against the same types of defensive positions. The soldiers reported that no cover was effective. The shells exploded above them, regardless of where they hid. Traditional artillery tactics assume that soldiers in trenches and foxholes have protection from airburst fire, because setting time fuses accurately is difficult. But proximity fuses eliminate that assumption. Every shell explodes at the optimal height automatically. There is no defense except to retreat beyond artillery range. The Oberst's face had gone pale. We need to inform the high command immediately. If the Americans are using these against ground targets across the entire front, Osenberg interrupted. They are. Intelligence reports indicate widespread deployment beginning in late December during the Ardennes offensive. We estimate that 20 to 30% of American artillery ammunition currently uses proximity fuses. That percentage is increasing as production ramps up and stockpiles grow. Bauer sat down heavily in one of the workshop chairs. Calculate something for me. If the Americans are producing 40,000 fuses per day, how many have they produced total since mass production began? Hartman did mental arithmetic. Production appears to have started in meaningful quantities in mid-1943, approximately 18 months ago. Assuming average production of 35,000 per day over that period, total production would be approximately 19 million fuses. 19 million, Bauer repeated. 19 million electronic devices, each containing a complete miniature radar system. And we sit here unable to manufacture even one working prototype. No one responded. What response was there? The numbers spoke for themselves. Osenberg walked to a filing cabinet and pulled out another folder. This contains a captured American document, a production schedule from Western Electric's facility in Kearney, New Jersey. The document is 3 months old, but intelligence considers it reliable. He handed the folder to Bauer. Western Electric employs 4,800 workers at that facility and produces approximately 12,000 proximity fuses per day. 12,000 from one factory. The document includes detailed cost breakdowns. Total program cost for developing and producing the proximity fuse system is estimated at approximately $1 billion American dollars. Bauer looked up sharply. $1 billion? For one weapon system? For one type of fuse? Yes. The Americans consider it money well spent because the fuse saves American lives and makes American weapons devastatingly effective. They can afford this investment because their economy is not being bombed. Their factories are not being destroyed. They have unlimited resources and time to develop whatever technology they need. The Oberst stood and walked to the window. His voice was bitter. We are losing this war, not because our soldiers lack courage, not because our generals lack skill. We are losing because the enemy can manufacture miracles while we struggle to produce ordinary weapons. Bauer stood as well. Dr. Osenberg, Prepare a complete technical report. Document everything you have learned. Include your assessment of German manufacturing capabilities and timeline estimates for possible replication. Forward copies to my office, to the Army Weapons Office, and to the Research Council. I will ensure it reaches appropriate decision makers. He paused, then added, though I suspect most of them will not want to read it, because accepting what this fuse represents means accepting that we lost this war years ago in factories and laboratories while we were celebrating tactical victories that no longer matter. After Bauer and the officers departed, Ozenberg and Hartmann continued working in silence. They finished documenting the test results. They photographed the components from multiple angles. They prepared specimen samples for shipment to other research facilities. Methodical work, pointless work, work that engineers did because it was what engineers did. Late in the afternoon, Hartmann spoke quietly without looking up from his notes. We captured our first proximity fuse in June 1944, 7 months ago. We have had 7 months to analyze this technology. We still cannot build a working copy. The Americans were producing these in massive quantities a year before we even knew they existed. He set down his pen. They won the technological race before we realized there was a race to win. Ozenberg packed the examination materials into a secure case. These would be sent to Berlin. More engineers would study them. More reports would be written. More meetings would be held. All of it absolutely irrelevant to the outcome of the war. He walked out into the January cold. The sun was setting behind heavy clouds. Artillery fire rumbled in the distance. Soviet guns to the east, American guns to the west. And now he knew that many of those American shells carried fuses that saw their targets. Fuses that exploded at perfect heights. Fuses that multiplied effectiveness by factors that made traditional artillery tactics obsolete. 40,000 per day, every day. While Germany's best engineers stood in cold workshops trying to understand how the impossible had become routine. The snow was falling again. Ozenberg lit a cigarette with shaking hands. He did not usually smoke, but 6 days of continuous failure, followed by the realization that failure was inevitable, had broken something inside him. Germany had the scientists. Germany had the engineers. What Germany did not have was the industrial system to turn scientific concepts into mass-produced weapons at the scale the war demanded. The Americans had that system. They had it operating at full capacity, and they had been operating it for years while German industry struggled under Allied bombing and resource shortages. Tomorrow, he would write his report. He would document the technical specifications. He would explain why Germany could not copy this technology. He would calculate that by the time German industry could potentially manufacture proximity fuses, the war would be long over. The report would be filed somewhere. Perhaps someone would read it. More likely, it would be forgotten in the chaos of defeat. It did not matter. The outcome was already determined by factories in New Jersey and Massachusetts and Ohio that could produce 40,000 electronic miracles per day. Determined by an industrial system that made the impossible routine. Determined by mathematics that could not be defeated by courage or skill or desperation. Ozenberg finished his cigarette and walked to his vehicle. The heater did not work. He drove back toward Berlin through the gathering darkness, past checkpoints manned by soldiers who did not yet know they had already lost, past refugees fleeing west from Soviet advances, past the ruins of Germany's industrial capacity being systematically destroyed from the air. Somewhere in America, factories were running 3 shifts per day. Assembly lines were producing vacuum tubes. Workers were installing them in fuses. The fuses were being loaded into shells. The shells were being shipped across the Atlantic, and German soldiers were dying under air bursts that exploded at perfect heights because American engineers had solved problems that German engineers had declared unsolvable. 40,000 per day. The number kept echoing in his mind. Not just a production figure, a death sentence written in mathematics and delivered by assembly lines that never stopped. Oberleutnant Hans Richter pressed himself into the frozen mud of his foxhole and waited for death. Above him, American artillery shells detonated in perfect sequence. Not on the ground, not after burrowing into the earth, in the air, 3 meters above the trench line, 4 meters, 5 meters. Each explosion sent shrapnel slicing downward into positions that were supposed to provide protection. Men were screaming, not the usual screams of wounded soldiers, something worse, the screams of men who understood they had no defense, no way to hide, no way to survive. January 4th, 1945, 2 kilometers west of Bastogne. Richter commanded what remained of the 3rd Company, 26th Volksgrenadier Division. He had 43 men left from the 120 who had started the Ardennes offensive 2 weeks earlier. They were dug into a defensive line along a tree-covered ridgeline, waiting for the expected American counterattack. The American artillery barrage had started 14 minutes ago. Richter had counted every shell, 57 so far, and every single one had exploded at the perfect height to kill men in trenches. This was impossible. Time fuses were inaccurate. Everyone knew this. You could set a fuse for air burst, but atmospheric conditions, powder variations, and manufacturing inconsistencies meant shells exploded at random heights. Most hit the ground. Some burst too high. A few exploded at effective altitude purely by chance. That was the mathematics of artillery. That was why infantry could survive in trenches. The odds favored the defenders. But these shells were not following the mathematics. These shells were exploding with perfect precision, every single one at lethal height. Richter raised his head slightly and looked down the trench line. Bodies everywhere. Men killed in their foxholes by shrapnel that had come from above. Positions that should have protected them had become death traps. Obergefreiter Schmidt lay dead, most of his chest missing. Gefreiter Holtzmann had no head. Feldwebel Kraus was draped over the parapet, his back shredded by fragments that had struck vertically downward. Another salvo arrived. 8 shells this time. 8 perfect air bursts spaced along the defensive line with mathematical precision. Richter pressed his face into the mud and felt something hot slice through the air centimeters above his helmet. A chunk of shrapnel buried itself in the trench wall next to his head. His ears were ringing, his hands were shaking, and his mind was calculating something he did not want to calculate. When the barrage had started, he had 43 men. He could now see perhaps 20 still moving. The rest were dead or dying. 1 barrage, 14 minutes, half his company gone. The American artillery shifted fire 200 meters south. Richter pulled himself out of his foxhole and crawled along the trench line, checking survivors. Unteroffizier Bauer was dead. Schütze Werner was alive but bleeding from 8 separate shrapnel wounds. The company medic was dead, killed in the first salvo. Richter reached his radio operator, Gefreiter Lutz, who was hunched over the radio set with blood running from his left ear. "Get me battalion." Lutz worked the radio with shaking hands. "Battalion Commander, Herr Oberleutnant." Richter took the handset. 3rd Company reporting. "We have sustained approximately 60% casualties from American artillery. Defensive positions are not effective. The shells explode above the trenches. Request permission to withdraw. There was a long pause. Then Major Vogel's voice came through, distorted by static and something else. Fear. All companies are reporting similar casualties. Second company has 70% losses. Fourth company has been effectively destroyed. We are withdrawing to secondary positions immediately. Leave the wounded. Move now. Richter gathered his survivors. 16 could walk. 4 could move with assistance. 7 were too badly wounded to evacuate. He left them with the remaining morphine and bandages, knowing they would probably freeze to death before medical teams could reach them. The withdrawal happened under continued artillery fire, more air bursts, more perfect explosions. Richter lost 3 more men during the 500-meter movement. When they finally reached the secondary line, he had 11 men left from 43, 74% casualties in less than 1 hour from artillery alone. 5 days later, the Americans attacked with overwhelming force. Richter's position came under artillery fire for 45 minutes before the infantry assault began. The air bursts were continuous, relentless. The few defensive positions with overhead cover helped slightly, but shrapnel still found ways through. When American infantry finally appeared through the smoke, they faced almost no resistance. Richter and 4 survivors surrendered after firing perhaps 20 rounds total. There was no point dying for a position that could not be held against shells that exploded at perfect heights. The Americans processed prisoners efficiently. Richter was searched, documented, herded to a collection point with several hundred other German soldiers. Most were wounded. All looked defeated. An American captain identified Richter as an officer and pulled him aside. The interrogation tent was warm, the first warmth Richter had felt in weeks. An American major sat behind a folding table, notepad ready. "You will answer my questions truthfully. If you cooperate, you will be treated according to Geneva Convention. If you do not, things become difficult, understand?" Richter nodded. "Describe what happened to your unit." Richter described the barrage from January 4th, the perfect air bursts, the devastating casualties, the complete uselessness of foxholes and trenches. The major made notes. "You understand what caused this? We learned later. Some kind of radio fuse. Detects the ground and explodes at correct height." The major looked up. "Proximity fuse." "Yes." "And what was German reaction?" Richter felt anger rise in his chest for the first time since the surrender. "What could be our reaction? We had no defense. You have created a weapon that makes defensive warfare impossible. Men die in positions that should protect them. What do you want me to say? That we admire American engineering? That we congratulate you for finding new ways to kill soldiers who cannot fight back?" The major set down his pen. "I understand your anger, but from our perspective, these fuses save American lives. They allow us to destroy enemy positions with fewer shells and fewer casualties on our side. They make the war shorter." He paused, then continued. "And they demonstrate something important. We developed this technology starting in 1940. 5 years ago, we went from concept to mass production in 3 years. We now manufacture 40,000 of these fuses every single day. That is why we are winning this war. Not courage, not tactics, industrial capacity." Richter said nothing. The American was stating obvious truth. Germany could not compete with enemy industrial capacity. The proximity fuse was merely one example among hundreds. The interrogation continued for another hour. Unit strengths, defensive positions, ammunition supplies, morale assessments. Richter answered everything. Resistance was pointless. The war was already over. They transferred him to a larger prisoner of war camp near the French border 3 days later. The camp held approximately 8,000 German prisoners in a fenced compound surrounded by guard towers. Conditions were tolerable. Food was adequate. Medical care was provided. The Americans followed Geneva Convention rules strictly. Richter was assigned to a barracks housing 40 officers from various units. Most were Army, a few were Luftwaffe, one was Kriegsmarine. They spent their days in enforced idleness, waiting for the war to end, waiting to go home, waiting for their lives to restart. On the evening of his 4th day in camp, Richter sat at a table in the barracks common area with 3 other officers. Hauptmann Ernst Kohler had commanded an anti-aircraft battery. Major Friedrich Schneider had led an infantry regiment. Kapitänleutnant Werner Brandt had served on a destroyer in the Baltic. They were playing cards with a worn deck provided by the Americans. The game was desultory. No one cared about winning. Kohler dealt another hand, then set down the cards. "I need to tell you something about these proximity fuses, something I learned before I was captured." The other 3 looked up. My battery was positioned near Bremen, protecting the naval dockyards. We had good crews, experienced men. We shot down perhaps 20 Allied bombers over 6 months. We considered ourselves effective. Then in September, everything changed. British bombers started attacking at night more frequently, and our shells stopped working correctly. "What do you mean stopped working?" Schneider asked. "We would fire at bombers crossing our sector. We would set time fuses for altitude. We would fire full salvos. Standard procedure. But we were not hitting anything. The British bombers were flying through our barrage zones completely untouched. We thought initially it was poor fuse settings. We recalculated. We adjusted. Nothing helped. We were firing hundreds of shells and achieving no kills." Kohler lit a cigarette with shaking hands. Then one night in October, British aircraft attacked German positions along the French coast. We monitored the engagement on radio. The British were using some kind of rocket against the V-1 launch sites, and they were achieving hit rates we could not believe. 80%, 90%, against targets moving at 650 kilometers per hour. "That is impossible," Brandt said quietly. "That is what I thought." But the reports were consistent. Multiple observers. British anti-aircraft fire was destroying V-1 flying bombs at rates that should not be possible. We later learned they were using American proximity fuses. The same fuses the Americans were using against our infantry, against our aircraft, against everything. He drew on his cigarette. We realized that the British bombers flying over Bremen were probably equipped with jamming equipment that disrupted our radar fire control. While we were firing blindly with inaccurate time fuses, they had technology that could hit targets at incredible rates. We were fighting with weapons from 1939. They were fighting with weapons from the future. The barracks fell silent. Someone was coughing in a distant bunk. The wind rattled the windows. Outside, American guards walked their patrol routes. Schneider spoke next. His voice was flat, emotionless. "My regiment fought in the Hürtgen Forest, November and December. The Americans attacked our positions with massive artillery support. The forest canopy was thick. We thought it would protect us from air bursts because the shells would detonate in the trees, too high to be effective against ground positions." He stared at his cards without seeing them. The first barrage killed 40% of my forward companies in 15 minutes. The shells were exploding just above the treetops, 30 meters up, 40 meters. The shrapnel came down through the canopy and killed men in their fighting positions. Trees that should have protected us became a roof that funneled death downward. After 3 days, the regiment ceased to exist as an effective fighting force. We had started with 2,100 men. We withdrew with perhaps 600 combat effectives. The rest were casualties, most from artillery. Artillery that exploded at exactly the right height every single time. One of my battalion commanders wrote in his final report that the forest looked like a giant scythe had cut everything above 40 feet. Trees were shredded, men were shredded, and we had no defense. Brandt was nodding slowly. He had not touched his cards. His destroyer was sunk in March 1944, off the coast of Norway. We were on patrol when American carrier aircraft attacked. We engaged with anti-aircraft fire. We had good crews. We put up heavy defensive fire. But the American aircraft kept coming. They were using some kind of rocket against us. Small rockets fired from under the wings, and every rocket seemed to find a target. They sank us in 8 minutes. He looked up at the others. I was pulled from the water by a Norwegian fishing boat. I spent 4 months recovering from burns. When I returned to service, I asked about the American rockets. Intelligence officers told me the Americans had developed proximity fuses small enough to fit in aircraft rockets. They could shoot these rockets at ships from 500 meters distance and achieve hit rates exceeding 70%. Our anti-aircraft fire was useless because we could not shoot down enough rockets fast enough. The German Navy lost most of its remaining surface fleet in 1944, not to Allied battleships, not to torpedoes, to aircraft firing proximity, fused rockets that we could not defend against. The technology gap was too large. We were fighting a war we had already lost years earlier. Richter listened to these stories and felt something cold settle in his chest. 3 different fronts. 3 different weapons, all using the same American technology that Germany could not match. The proximity fuse was not just one weapon. It was an entire category of weapons that had made German defensive tactics obsolete across every theater. A new prisoner arrived at the barracks 2 weeks later, Oberst Paul Richter. No relation to Hans, but they shared the same surname and bunked near each other. Paul Richter had been a staff officer at Army Group B headquarters. He had access to intelligence reports that frontline officers never saw. They spoke one evening after the barracks lights were dimmed. Paul's voice was barely a whisper. "I need to tell you something you will not believe. In December, just before I was captured, I saw a report from the Army Weapons Office, a technical analysis of the American proximity fuse. Do you know what the report concluded?" Hans shook his head. Germany also developed a proximity fuse. We called it the Kranich fuse. Development started in 1942. The scientists at Telefunken built working prototypes in 1943. The technology was proven. It worked. Hans felt his breath catch. We had this technology. We had it, but we could not manufacture it. The fuses required specialized vacuum tubes that our factories could not produce in quantity. They required miniature batteries that did not exist in German production. They required manufacturing precision that our bombed factories could no longer maintain. We built approximately 8,000 prototype fuses by early 1945. The Americans built 22 million. Paul was silent for a moment. The report I saw included cost comparisons. Each American proximity fuse cost approximately $18 to manufacture. Each German Kranich fuse would have cost approximately 250 Reichsmarks to produce, roughly $100. We could build fuses that worked. We could not build them at a price that made military sense, and we certainly could not build them at a scale that mattered. The Americans were producing these fuses for less money, and in quantities 1,000 times larger than we could achieve even under ideal conditions. That was the true measure of the industrial gap. Not that they had better scientists, not that they had better engineers. They had better factories, better supply chains, better manufacturing systems, better everything. Hans lay in his bunk that night, staring at the ceiling. Germany had possessed the technical knowledge to build proximity fuses. German scientists had solved the engineering problems. But German industry could not translate that knowledge into weapons at the scale required to effect the war. The Americans could. They had. And 22 million proximity fuses later, Germany was defeated. The war ended in May. Hans Richter remained in the prison camp until September 1945. He was finally released and repatriated to Germany in October. He returned to a nation in ruins. His family home in Bremen had been destroyed by Allied bombing. His father was dead. His mother lived with relatives in the countryside. His younger brother had been killed at Stalingrad. Richter found work eventually. Labor was needed for reconstruction. He worked construction jobs. He helped clear rubble. He rarely spoke about the war. When asked, he would say he had fought and been captured and survived. He did not describe the artillery barrage from January 4th, did not explain how proximity fuses had killed most of his company in 14 minutes. But sometimes, late at night, he would remember the perfect airbursts, would remember counting shells and calculating casualty percentages, would remember the moment he understood that courage and training and experience were irrelevant against an enemy who could manufacture miracles. In 1952, Richter attended a memorial service for soldiers from his division. An elderly general gave a speech about sacrifice and duty and honor, about how German soldiers had fought bravely against overwhelming odds, about how history would remember their courage. Richter sat in the audience and thought about proximity fuses, about 22 million of them, about American factories producing 40,000 per day, about German scientists who had developed equivalent technology, but whose factories could not produce it at scale, about a war decided not by courage but by assembly lines, about mathematics that killed without mercy and without end. The general finished speaking. Everyone applauded. Richter applauded too. But he was thinking about something Paul had said in the prison camp, something that haunted him more than the screams of dying men. We had the knowledge. We lacked the capacity. That was the epitaph for the entire war. Written in statistics no one wanted to remember. Carved into mass graves no one wanted to visit. Delivered by shells that exploded at perfect heights because one nation could manufacture miracles while another could barely manufacture ordinary weapons. 40,000 fuses per day, every day, until Germany surrendered, until the killing stopped, until the mathematics finally ended.